Today we're doing a double replacement reaction with magnesium sulfate, that's Epsom salts, and calcium chloride, which is used as a road de-icer and for vegan caviar. We are going to dissolve these both in water separately and mix them together and see what happens. Ready? Magnesium sulfate and calcium chloride are both water-soluble ionic compounds consisting of a positive ion, the magnesium and calcium, and a negative ion, the sulfate and chloride. When these compounds are put into water, they break apart into their respective ions. We already know that magnesium sulfate and calcium chloride are water-soluble, and so is magnesium chloride, so any of these combinations will simply dissociate apart again. However, calcium sulfate is much less soluble in water than any of the other combinations, so when a calcium ion interacts with a sulfate ion, they will stay stuck together. The white stuff that we see forming is that insoluble calcium sulfate. This is an example of a double replacement reaction in which the ions of two compounds switch places. Both of the reactions must be soluble or they won't be able to interact. In order for something to be considered a double replacement reaction, one or both of the products must also come out in a different form, either as a gas or as a solid precipitate. In this case, it's a solid. We can predict whether a double replacement reaction will occur based on rules of solubility. The simplest way to do this is to check the compounds using a solubility table. For instance, all ionic compounds of group 1 elements are water-soluble, so if you have a salt that contains one of these, you know it will be soluble in water, and you can stop there. Ammonium salts are also always soluble in water, as are acetates, nitrates, and bicarbonates. These trends take priority over other trends. For instance, Phosphates are usually insoluble unless they are combined with a group 1 element or ammonium. Most halide salts, salts containing a group 17 ion, are soluble except with silver 1, mercury 1, and lead 2. One challenge arises, which is that just because two things are soluble doesn't mean they're equally soluble, and sometimes you will find tables that disagree about whether a particular compound is considered soluble or not. Some charts do not list calcium as an exception to the rule that says sulfates are soluble, but as we've just seen, this reaction produces a precipitate. That's because calcium sulfate technically is soluble. Very few things are actually completely insoluble, but its solubility is much, much lower than other compounds. The CRC handbook lists the solubility of magnesium sulfate as 35.7 grams per 100 milliliters of water at 25 degrees Celsius, or about 3 moles per liter. The solubility of calcium chloride is 81.3 grams per 100 milliliters of water, or about 7.3 moles per liter, and the solubility of magnesium chloride is 56 grams per 100 milliliter, or about 5.9 moles per liter. But the solubility of calcium sulfate is only 0.205 grams per 100 milliliters of water, which is only about 0.015 moles per liter. So technically, a small amount can be dissolved in water, but it's a very small amount. You should know how to use a solubility table, but there are already many videos out there that walk you through how to do this, so I won't spend a lot of time going over that. You could also try to memorize soluble and insoluble compounds, but that would also be a lot of work, and it doesn't really help you understand solubility very much. While I've seen a lot of resources explaining how to use solubility tables, I've seen very few give any kind of explanation for why these trends exist in the first place. So I want to talk a little bit about some of the factors that go into what makes a compound soluble in water or not. First, let's review the basics of what we're talking about here. A salt is an ionic compound made up of a positive cation and a negative anion held together by an ionic bond. Water, our solvent, is an example of a polar molecule. The oxygen in the water is much more electronegative than the hydrogens, though not quite enough to be ionic. The oxygen and its lone pairs therefore carry a partial negative charge, while the hydrogens carry a partial positive charge. This polarity is what is responsible for a lot of the unique properties of water, like cohesion and adhesion, although that is a topic that deserves its own separate discussion. Most importantly for this video, the polarity of water is what makes it such a good solvent of polar and ionic substances. Even though they aren't full charges, the partially charged regions of the water molecule can interact with charged regions of other things, and it will exert a force on them. The partial negative charge on the oxygen of the water will be attracted to the positive ion in an ionic compound, or to the partial positive on a polar substance, and the partial positive on the hydrogens will be attracted to negative ions or regions. In contrast, a polar substance like water is a poor solvent for nonpolar things like hydrocarbons, where the charge is distributed fairly equally across the molecule, because the forces between opposing poles of water molecules will cause water molecules to be more attracted to each other while ignoring the nonpolar molecules, which hold little attraction for them. This is why oil and water don't mix. Eventually I'll make a video about how soap helps you overcome this to wash greasy dishes, but that's also a topic that deserves proper time of its own. So this is why water can solvate ionic compounds. But going back to our original question, why are some ionic compounds more soluble in water than others? Well, there are a number of factors. Unfortunately, they're not super straightforward, and it's not really a cut and dry case of one factor completely determining the solubility of the compound. But let's take a look at these trends. One of the most important components here is the strength of the ionic bond itself. Salts form neatly ordered structures called lattices made up of alternately arranged positive and negative ions. Sometimes these lattices are very strong, sometimes they're weak. Whether a lattice is strong or weak first depends on the strength of the ionic bond, which can be found with Coulomb's law. Force equals K, which is Coulomb's constant, times the charge on one particle times the charge on the second particle, all over the distance between them squared. Just like two magnets are harder to pull apart when they're closer together, the closer two ions are able to get to each other, the stronger that force will be, and the farther apart they are, the weaker that force will be. Doubling the distance between two ions will quarter the force, while halving the distance will quadruple the force. So generally speaking, the smaller the ions are, the stronger the force between them will be, while larger ions will have a weaker force, because they aren't able to get as close to each other. Remember how we said the group 1 and most of the group 17 elements were highly soluble? That's because these ions are pretty big. The other set of variables at play in Coulomb's law are the charges. Group 1 elements form ions with a charge of +1, and group 17 elements form ions with a charge of -1. We use the absolute values in this equation, so that means Q1 times Q2 equals 1. If one of these ions had a charge with a magnitude of 2, that would be 2 times 1, or twice the force. If both of these ions had charges with magnitudes of 2, that would be 2 times 2, or quadruple the force. We said at the beginning that phosphates are almost all insoluble, which makes sense because even though phosphate is a large polyatomic ion consisting of a phosphorus and 4 oxygen atoms, it has a charge of -3, which makes that pretty strong. The ammonium ion, on the other hand, which is a nitrogen and 4 hydrogens with a total charge of 1+, is both large and has a smaller charge, so it makes very soluble salts. Size and charge are also related to each other because even though Coulomb's law treats charged particles as infinitely small points, these ions do have a size, and the charge on the ion is distributed across that size, so a large ion with a charge of magnitude 1 will have a lower charge density than a smaller ion that also has a charge of magnitude 1. This explains some of the rules, but it's not as straightforward as just looking at what ions are the biggest or the most charged. Calcium sits below magnesium on the periodic table. The periodic trends for both atomic radius and ionic radius say that things get bigger as you go down a column, which makes sense because when you're going down the table, you're adding more shells of electrons like layers of an onion. So calcium is bigger than magnesium, and since they're both in the same group, they also both form ions that have the same magnitude of charge, 2+. Based on Coulomb's law alone, we would expect that calcium sulfate would be more soluble than magnesium sulfate, because while the charges are the same in both cases, the distance between the calcium and sulfate ions is greater than the distance between the magnesium and sulfate ions, which makes that force weaker. But obviously that isn't what we see. So what gives? We have to go back to that lattice structure and the reason why water is a good polar solvent. The lattice energy, which is the force holding that lattice structure together, is only part of the picture. The other part of the picture is the solvation itself. It's all fine and good to say that magnets require less force to pull apart when they are farther away from each other, but if you can't actually get to the magnets to pull on them, that's moot. It turns out that the calcium ion is much closer in size to the sulfate ion than the magnesium ion is. The sulfate ion is about 240 picometers. The calcium ion is about 115 picometers, while the magnesium ion is only about 80 picometers. So there's more dead space in which the water molecules can maneuver and interact with the ions in the lattice to pull them apart from each other. A similar concept that is easier to imagine is the relationship between surface area and the time it takes for something to dissolve. Which would you expect to take longer to dissolve, 10 grams of ordinary table salt or a single 10-gram chunk of rock salt? The amount of sodium and chloride ions that can eventually dissolve in the solution will be the same regardless of how big the pieces of salt are, but it's going to take a lot longer for the large chunk to dissolve than for the small grains, because the small grains have a much larger surface area to volume ratio. The water molecules are going to interact with the ions on the outer surface of the crystal lattice. They can't really get to the inner layers until the outer layers have been dissolved away. For small grains of salt, this isn't going to take very long. For giant crystals, it will take a long time for the water to solvate the entire thing. Also, while it's true that the attractive force between the smaller magnesium ion and the sulfate ion is stronger than between the calcium and sulfate, it's also true that the attractive force between the smaller magnesium ion and the water molecules is greater due to magnesium's smaller size. Lastly, The attractive forces between opposite charges are not the only forces at work in the lattice. There are also repulsive forces happening between like charges. When your ions are closer together, you have stronger attractive forces between the opposite charges, but you also have stronger repulsive forces between the like charges. So when these ions are close together, you also have to factor in the stronger forces that are pushing the like charges apart. The degree to which this affects the overall strength of the lattice is highly dependent upon the specific atoms and the specific structure involved. So the bad news is that there are multiple factors at play, and you can't necessarily reason out which compounds will be soluble based solely on charge or size, which is why we have solubility tables in the first place. And it gets even murkier when you start to move away from the ends of the periodic table and into the transition metals, due to things like the placement of their valence electrons. But hopefully you now have some conceptual idea behind what's happening, and the topic of solubility is at least a little less cloudy than the product of our double replacement reaction. Remember kids, if you aren't part of the solution, you're part of the precipitate. Well, I think I'm funny anyway.